So hello everyone, I'm Kartik. The presentation is based on the stuff that I read for my undergraduate thesis with Professor Bhattacharya. I unfortunately missed Devashree's talk in the morning, and I expect there will be some overlap there, but hopefully there's sufficiently novel scientific import here. I felt silly in the morning after uploading the slides that, oh, I don't need to sell why it's worth studying neutron stars in a conference full of people who are talking about neutron stars. But one of the reasons why I was interested in them was because they lie on the intersection of so many domains of physics, because I'm primarily interested in general relativity. And I have absolutely no idea what's happening with the hadronic equation of state, research programs and those sorts of things, but I could still find some problem there which I found interesting. So my talk is about polarization, and polarization carries information about the mechanisms which produce the radiation at the neutron star. But the problem is that we don't see neutron stars as that extended object, right? We only see them as point sources. So, and additionally, as I would sort of explain further, there are all these effects which distort the polarization information before it reaches the observer. So what is emitted is not exactly what we see. And the question that I was interested in is, so given a pulsar configuration, what polarization data should we expect from it, and also vice versa. So if we do polarimetry on these isolated neutron star pulsars, what should we expect, and how do we get back the original data? So, well, obviously the neutron star attributes such as the angles between the spin axis and the magnetic dipole, or the angle between the spin axis and the observer, these sorts of things influence the kind of pulse profiles that we can expect from it. For example, the top blue line would be a pulsar which we're looking sort of parallel to the spin axis, and that's why we don't see any variations there. But these angles and these neutron star attributes can affect the pulse profiles. And well, if we have a clear enough understanding of what is the dependency between these attributes and the polarization data, and then we can perform inferences in various ways to extract from the pulse profile the original information. I said that there are all these effects which distort the polarization information which is emitted, and one of the main components there is the fact that neutron stars are really compact objects, and we expect gravitational lensing from them. So the problem is that as the light rays bend around the neutron star surface, the polarization vector themselves get rotated as the light ray is bending. So one, we simply just see more of the surface at once, so we have to account for more of the polarization attributes instead of just a simple projection. And the other thing is that the polarization vectors themselves are getting rotated. Fortunately, we understand light propagation in Schwarzschild geometries really well. The only problem is that explicitly ray tracing every single ray from every patch on the neutron star surface for every possible spin period, and then doing a Monte Carlo chain, a Markov chain on this is just really horribly computationally intractable. But there's this approximation that Beloborodov introduced, which relates so the angle with which the light ray needs to bend to reach the observer, and the location on the neutron surface where the angle is being emitted from. These are the two quantities that this approximation relates, and that is essentially all we need, because we need to know from any given patch which has a certain polarization property, how much does it contribute to the integrated sum or to the integrated flux in that polarization filter. So we get this, and then once we have this, we don't need ray tracing anymore. And with an improvement to the original Beloborodov approximation that we worked on in my thesis, the errors sort of remain under 1% throughout. These are just some results which show just how good the approximation is. On the left, you can't even see that there are 3 different lines which compare the exact ray tracing solutions to the Beloborodov approximation and the modified Beloborodov. But you see that as the neutron star becomes more compact, the approximation, the Beloborodov approximation starts struggling a bit, but after the modification it remains under 1% throughout. So now if we return back to the original question that given a neutron star pulsar configuration, what polarization do we expect? My answer to this came in the form of this polarization transport code that I've developed as a part of my thesis. And I'll just quickly sort of briefly go over how the code is structured. So I start with defining a neutron star object by giving it some properties, some characteristic angles, the compactness, magnetic field strength, those sorts of attributes. Then there's a physics module which accounts for quite a few physics effects, but you can always add more. But some of the things that it does is it accounts for the gravitational lensing, of course, some redshift. It has a dipole magnetic field, and then it transfers the Stokes parameters and then does a surface integration, does an integration of all the patches of the neutron star surface that you should be able to see. And then you can define an observation, a virtual observation of some kind. So what is the phase range that you want to look at? What photon energy, what polarization filter have you stacked onto it? And it gives you the simulation results, which are essentially pulse profiles and specific polarization filters. And of course, you can do these, so the way the code is written is that it does all these things in parallel. So for example, on the 6 cores of my laptop, I can do 6 of these virtual observations in parallel. And you can define a whole catalog of objects, and then in principle, if you want to do an inference, you can sort of try to constrain parameter space by simply just seeing which objects in the catalog match the observations. And for now, I just said that, oh, there's this physics module, and I didn't really talk about what's happening in the physics module. And I still won't talk about what's happening in the physics module, but I added the next horrible looking slide just in case anyone has specific questions about what's happening, but here's sort of an overview of some of the things that the physics module does. We can come back to it if there are questions, of course. And here are some of the results, right? So, on the y-axis we have the degree of linear polarization represented in percentage. And here are some possible neutron star geometry, choices of characteristic angles. And well, for some sanity checks, of course, if you're looking at it parallel to the spin axis, then you shouldn't expect any variation, which is what these solid lines represent. But also, another sanity check is that the maximum degree of linear polarization we expect when the spin axis is offset from the magnetic dipole axis by 90 degrees, and that's what we also notice here. But there are other physical parameters which affect the kind of polarization pulse profiles that we'll see. So one of them obviously is the compactness, because as I said earlier, the more compact the object is, the more is the effect of gravitational lensing there, and the more of the surface we see at once. So because we're seeing more of the surface at once, the different polarization, the different polarization attributes get mixed, and then the total degree of linear polarization drops. So for a more compact object, we expect lesser degree of linear polarization, and that's what we see here as well. And this might be one of the strongest pitches to do polarimetry of these objects, because then it can help us constrain the mass radius relationship, because compactness is an important piece of the equation of state puzzle. And then there are other physical parameters that you can just vary straight up, just download the polarization transport code from the GitHub and then play around with these things. There are also certain degeneracies that are immediately obvious to us. For example, if there's a neutron star which has an order of magnitude stronger magnetic field, but we're observing at it at an order of magnitude lower energy, then we essentially get the same pulse profile, same characteristic of the degree of linear polarization. But well, we don't have to just look at them in one specific energy band. We can have multi-wavelength observations. This is just simulated data. So a lot of this was done in anticipation of EXPOSAT data, which is an Indian mission to do X-ray polarimetry of these of such objects. There's also XP, which does X-ray polarimetry, but I'm not sure whether they looked at isolated neutron stars, but I might be wrong. I'm just very bad at this observational stuff. But I suspect that people have asked for time on EXPOSAT at least to look at isolated neutron stars and do polarimetry. Also, the energy ranges are slightly different for both of these. And that sort of brings me to the end, where I'll just quickly go through what are the ways in which this can be extended. This was a lot more relevant last year when I was freshly graduating, but now I do cosmology, so it's not. It's more of an embarrassment that this hasn't been done yet. But the point is that that the green things are sort of completed, and then there's the dashed green line, which is so. For example, this is done. This data has been simulated with a very naive spectrum, but we can do more complicated radiative transfer, of course, and for these neutron star atmospheres, and we can also have more sophisticated surface intensity maps with like specific choices. Do you want a Gaussian on the hotspots? Do you want a hollow cone? And those sorts of things. So these are sort of there in the code, but they haven't been tested properly yet. But then also Jagat Kafle, who also did his, who defended his undergrad thesis last week, who also worked with Professor Deepankar, has written a custom code for doing radiative transfer, which interfaces with the existing transport code. And then you can also add further effects which would expect which you would expect distorts polarization information, like vacuum birefringence. So that has to be, like, someone needs to think about whether or not it's worth adding. And then the last thing which is certainly worth adding is that for now, the way the code is parallelized is that it does a single observation in parallel per each core. But then if you have lots of cores, as in a GPU, then you can essentially do the transport and surface integration at once instead of sort of iterating through every patch of the neutron star surface. So that would greatly help if people want to do inference later, and well, that's it. Yeah.
Questions?
I don't think you can disentangle. I think it can be used as a supplement to other observations to break degeneracy. But
right.
Yeah, like mass and radius individually do not affect the polarization profiles. It's the compactness which does. So yeah. Yeah. So well, one the magnetic field is dipole, of course. It's a dipole in a Schwarzschild, so the dipole gets disrupted because of the general relativistic corrections, which it does account for. That's the expression which the code uses. And then for the variations in hotspots, as I mentioned, so the way it works is that there are the IO and IE, which are intensities in ordinary and extraordinary modes. And then you can define a surface map of intensity in which you can define what kind of a hotspot do you want there. So you can have, there are some choices which are already there in the code. So you can have some, like you can play around with the size of the hotspot and how sharply do you want it to fall and those sorts of things. But I haven't tested those things too well yet, so I wouldn't trust them very much. Yeah, so what happens with polarization transport in these, like, so the way this was solved was you literally just take the polarization 4 vector and then you solve the geodesic equation for it, and then you can basically relate the two coordinate frames. But this was one of those things which I was confused when I was starting. I thought that there's an active process which is kind of like a birefringent material where the polarization rotates. That is not what is happening in this general relativistic understanding of polarization transport. It's just the light ray itself bends and the polarization vector basically bends along with it because it has to stay constrained within a certain geometry. So yeah, but there's no, it doesn't rotate it in the sense of birefringent material rotates it. It's more of a geometrical effect. Yeah.
Okay, then thanks a lot.
Okay. Yeah.